Hello, welcome to COMSOL Tutorials Hub. My name is Amin and I have a master's degree in mechanical engineering from Hajj Nasir University. Please subscribe our channel for more tutorials. You can contact me through the links provided here. Welcome back to the second part of our tutorial on modeling the microchannel heat exchanger in COMSOL. In this video, we are going to take the next step by adding the physics to our model, defining the boundary condition based on our reference paper, and finally meshing the geometry. As you can see in tutorial part 1, we define geometry, parameters, variables, and we define our materials for solid and fluid. We used aluminum nitride for solid and we used water for our fluid, as our fluid. Okay, I will begin by adding the physics interfaces one at a time. First, we add the laminar flow physics to simulate fluid flow inside the channels. Then we'll add the heat transfer in solids and fluids interface to capture how heat is exchanged between the fluid and the walls. In first step, we should define our initial temperature. It's at room temperature. Next, we add for laminar flow, we add two inlet condition. It's our cold inlet. I specify upstream absolute pressure also. I should rename it to cold inflow, cold flow, and we will add the second inlet. We should define upstream temperature and specify upstream absolute pressure. It's also it's hot inflow, 90 degree, and we should give a hot flow name to this boundary condition. Okay, now we should add it to outflow condition. Okay, for our cold, we need a outflow condition. Let's first rename it to outflow. We are specifying the temperature boundaries at the inlet and outlets as per the validation paper, same as the validation paper. Okay, well done. I'm checking again, and also we should use the symmetry conditions where necessary to mimic the physical scenario. Okay, for the laminar flow, we need to set up the inlet boundary conditions for cold and hot fluids with the appropriate mass flow rates. I will define the outlet boundaries where the pressure is set, usually atmospheric, and we will apply the no slip condition on the channels wall. For inlet 1, it's a for cold flow passage. M cold is a parameter that I defined in the parameters section. Let's choose boundaries for the cold flow passage. In boundary condition section, I first choose mass flow and I define normal mass flow rate. After that, I rename it to cold water. Let's rename this too. It's a hot water that flows in the channel. And now we should define the outlet boundaries where the pressure is set. For atmospheric pressure, we should set it as 0. Static pressure, I'm checking which boundaries are for cold flow passage and which are for hot flow passage. Let's rename it to cold water outlet. Okay, and we should define a second outlet for hot water, same as before. So easy. Okay, done. We don't need to use symmetry in laminar flow. So let's go to the next step, multiphysics. This multiphysics will couple these two physics. For convection heat transfer and diffusion heat transfer, we need to couple these two physics. This multi-physics will do this. Okay, first I used automatic mesh, but I will change the options. Let's first have a free triangular mesh on this surface. I don't like this because there's some big parts at the end. Let's change it to finer. It isn't changed. Okay, maybe extremely fine will help us. No. Extra fine. Aha. This was coarse. We've used a combination of different meshing techniques here. You can see we have a free triangular and free quad, and I will use swept mesh. I use free quad for fluid domains. The swept mesh is particularly useful for structured grids in fluid flow simulations, helping capture variations in velocity and temperature across the layers. And this, let's check the paper mesh. Okay, I think our mesh is good. You can see a corner refinement. This has been applied in specific regions. This is especially important in areas with sharp edges or complex flow patterns to improve solution accuracy. Okay, yeah, now good. Let's increase the number of triangular mesh. Maybe I use extremely fine. It's better now. It's better now. Oh, so it's good. It's fine. Now let's move to. Let's check it again. Let's move to swap mesh. Nice, I like it. Let's delete this. For swap mesh, we should choose source faces and destination faces, where the mesh starts and ends. And we should check and choose domains we want to as source faces and destination faces. Let's check the fluid domains. Fine mesh captures small details but increases computational time, while a coarse mesh runs faster but may miss critical physics. The goal is to find the right balance, refine enough mesh where the results do not change significantly with further refinement. We are balancing now. I think it's good. I was still working on a mesh to have better mesh for our geometry. I think now it's good, and I'm satisfied with it. Now let's move on to parametric shape section. What we are doing here is varying the mass flow rate of the cold and hot fluids, M cold and M hot, to see how the system behaves under different operating conditions. The parameters value are given in kilogram per hour, covering a wide range to fully explore the heat exchanger heat exchangers performance. This helps us to analyze heat transfer efficiency, pressure drop, and thermal behavior for different flow rates. In the study settings, you can see that we've selected specified combinations under the sweep type. This means that COMSOL will run simulation for each combination of cold and hot automatically. I run the simulation, and for the results you can see the part 3 of our tutorial. Please subscribe our channel for more tutorials. Thank you.